This is the 8th experiment in Charles Platt's Make Electronics 2nd edition, a relay oscillator. They will be using a new component, which is a capacitor. Particularly, it's a 1000 microfarad capacitor. It's the largest capacitor in the Cheney Electronics kits. If you don't have a 1000 microfarad capacitor, we'll be using some of the other large value ones as well. We'll also be using the slide switches, like a toggle switch, but actually fits into a breadboard. More on breadboards in a moment. Some fairly low value resistors, 470 or a kilo ohm. Of course, we'll need a 9-volt battery. To test that your switches are okay, it's very similar to the toggle switches, just harder to do with probes. The outside 2 pins should never have continuity when the switch is in isolation, whereas if you measure from the center to the left or the center to the right, you should find that the continuity will depend on whether or not the switch is on that side. Now, unlike the toggle switch, which has a lever sort of action, the slide switch, when it's pushed to the right as shown, should connect the center and right pins. There we are. Continuity. And you should have no continuity on the left 2 pins. When you slide the switch over, which can be done once in a breadboard with a pencil, for instance, now the left 2 should have continuity. And the right 2 should be open. That's how the little slide switch works, just like the toggle, but reversed in direction. Check our resistors real quick. Read the code, but then try to double check it with your meter. About should be a 470 ohm resistor. Might end up using a couple of them today. All right. We're going to use both a green and red LED. The textbook just calls for 2 red LEDs. I'm going to use a red and green because it's easier for me to talk about. Feel free to use your green or yellow if you wish, in addition to a red, or make them both red if you'd like. Of course, the green's just like the red. It's got a long leg and a short leg. And I want to point out another way of telling the polarity of your LED. There's a flat edge on the side of each LED. And if you roll it with your finger, you'll feel the flat edge, even if you can't quite see it. And that's going to be true of most LEDs. It's true of this green one here as well. It's got a small flat edge. And that can help you identify the polarity, say if you've cut your legs or you can't tell if one's shorter than the other. Of course, the other way to do it is to build a quick circuit and just to test the lights. We'll be doing that using the breadboard today. We'll need our relays, and we're going to start using a battery strap today for the 9-volt battery. So click those on. Should snap into place. Sometimes snaps so firmly it's hard to pull it off without damaging it. And then you'll notice what's happening to my leads here. They're kind of floating close together. You really don't want that to happen. We know what happens when you short out a battery. So don't let that happen with your leads. Once you've attached your strap, try to be cognizant of where your leads are. Switch your voltmeter now over to the 20 volt reading DC. And let's check our battery voltage through the strap. It should be close to 9 volts. Okay. Grab a couple of alligator clips. I like to use the red and black ones for this purpose. And we're going to start using the breadboard today. So there is a diagram in your textbook, figure 265, which shows a variant of a breadboard. What they have underneath, sort of an X-ray view shown in the textbook, is bus bars with a crack in between on the sides. To get a better idea of what it looks like, I actually happen to have a breadboard that's got its back removed, just like the textbook. So there's the breadboard, and there's the back side. Now, the reason we use breadboard is it makes it a lot easier and more convenient than alligator wires to clip things together. So if we look at the breadboard, we see it consists of both narrow rows, and then the long stripes on the side, long stripes I call bus bars. And when you insert a component from the top of the breadboard, it makes a connection through this bottom. Now, you don't normally see this X-ray view, so there's these short rows, which are here. So those are all connected. Anything you put in a row will connect to everything else in that row. And there's a break down the middle for inserting components across the row, right? So there's a break line you see in the middle. So the row on the top and bottom, they don't connect to each other. The bus bars go all the way across. Now, unlike the diagram in the book, most our breadboards today actually have 2 bus bars on each side. They're not connected to each other, and they're not connected to the rows, and there's a break often in the middle, but not always. So they don't connect across the break. And we're going to jumper that break out, so it's always connected today. So there's the 2 individual rows, and we usually use those for distributing power to components. We'll practice all this today. But again, there's that break usually in the middle. Here's a typical single breadboard, probably like the one you're going to be using. And I'm going to do a continuity measurement, and I'm just going through with a couple of wires which have been attached to alligator clips. Oh, continuity when I'm in the same row. And otherwise, open circuit. Continuity in the same row, otherwise it's open. Now, when I'm next to each other in this direction, there is still open circuits. So I can be in that column, no continuity, but there is continuity in the row. Jumping across the break, no continuity. So you can see the pattern follows exactly that X-ray pattern shown in the textbook. And I really encourage you to spend some time with your continuity meter, seeing when you do and do not have a connection. Connection, no connection. There's no connection over to the bus bars unless you make it yourself. As shown here. On a bus bar, there is continuity, but not to another bus bar and not to a row. Continuity there. Continuity, continuity, continuity. Go across the break. Suddenly no continuity on most meters. Again, this on most breadboards. It can vary. So you can see there's where the break is. There's an overload, meaning an open circuit. Whereas when we're on the same side of the break, continuity. So it's very important to understand where this is. Again, there's the break in the breadboard because there's no wire underneath. So it is literally a white box. You have to really understand where the connections are to make things work. We're going to make some jumper wires. I'll be using a fancy clipper. Here's the procedure that the book gives: is cut a little bit of extra off one edge of wire, find the proper pressure with which to strip the wire, and then leave yourself an amount of insulation on one side that's going to be related to the number of holes in the breadboard you want to jumper. And then pull that insulation out and make it nice and symmetric, and then bend 90 degrees till your jumper wire fits conveniently down on the breadboard. And I'm going to jumper across that upper red bus bar. So there's no longer a break. I have effectively undone the break that's in there, and now you should have continuity from one end of the breadboard to the other. Let's do that to the blue side, and we'll do it to the 2 bus boards on the bottom as well. Gives a little more practice making jumper wires, something to do quite a lot of. Again, you pull double the amount of insulation you want off one end, just as shown in figure 264 in the textbook. Cut an amount, leaving the desired amount of insulation, which should be the length of the number of holes you want to bridge. Make some 90-degree bends. Sometimes it gets a little hard to do those by hand, and so a device like a needle nose pliers is really great for making nice sharp bends. If you have a needle nose pliers, you'll find it comes in really handy. Suggestions on needle nose pliers are back in beginning of chapter 2 in the book. Now, I usually use red on the red bus boards, and I'll use them for carrying, say, the plus 9 volts on my battery. And I'll use a blue wire or black wire for the blue bus bars, which usually I'll connect both of those to the minus terminal or ground in a circuit. So I recommend you spend some time and prep your breadboards as shown. I should note that in today's video, because we're learning breadboarding seals for the first time, I've really sort of slowed things down, and we're going to take our time today and make sure you have the right dexterity skills here developed so that you can get things in and out of breadboard securely. A failure to insert those wires fully is one of the main causes of frustration at this point in electronics. Okay, one more bus board connection for the top of your circuit board. Once you've made connections, it's a really good idea to try to check them. Notice I have got a couple of little wires on my alligator clips that lets me just go around and probe the circuit and make sure I have continuity where I should and not where I don't expect it. Now, because I'm going to be using very simple power supplies for most of this class, namely just a 9-volt battery, I'm going to jumper together both red bus bars and both blue bus bars on one end of the breadboard. You can use either end you want. You don't have to do this, but I find this to be really helpful, especially when just getting started with a project, to make sure I've always got power on either side anywhere I want it. The whole idea of a breadboard is to avoid running lots of cables, so we let the wires underneath the board do the work for us. So I'm going to connect the red to the red, one end. Notice I really do try to cut my cables to length and then bend them to keep them out of the way. You can use long jumper cables of an arbitrary size. Some of your kits might have such cables, but cutting them to length is really, really helpful. Notice now I have continuity between the two bus bars, top and bottom. Just do the same for the negative. With the longer wires, sometimes I strip the insulation individually on each side. The short ones, I always try to cut a long chunk of insulation off first and then slide it. There we go. So now I should have the negatives attached on both and the positives attached on both. Now I'll just check it out real quick. Red to red continuity, blue to red no continuity, blue to blue continuity. Okay, now let's attach our battery. Now our battery can sometimes have some kind of weak or small threaded wires, or sometimes be too flexible or not long enough and can be a little bit hard. But the idea is to attach them into the bus board, and I could put it either way. I'll just use the top here. For starters, black onto the blue bus board, red onto the positive. But in fact, I'm going to try to gently remove a little bit more insulation, try to get a better connection in there. Sometimes twisting the wires a little bit together. We're eventually, once we get to soldering, going to make better connectors for all our batteries. But for now, you just have to kind of wiggle them in there. And you should start to have a feel for how long you have to get that wire and what it feels like to make a good connection. That's one of the main things you want to be sure you've done today. To get a feel for how much wire you have to push things into the breadboard. And of course, try not to leave exposed bare wire on top of the breadboard. That can lead to unexpected short circuits. Twist the wires up and try to make as good a connection as possible. So now we expect that everywhere on our breadboard on the bus bars we have plus 9 volts and 0 volts. We're going to move our voltmeter back over to the voltage setting away from continuity. I'm going to plug one of the red leads into a red bus board, red bus rail, and blue into another. And there's my 9 volts from the battery voltage. No volts when they're in the same bus bar. And I'll check the other side as well. Make sure I have power distributed everywhere. So this is prepping your bus board, and of course, there's no voltage that's being sent right yet over to the horizontal bars. Get comfortable again where there is and isn't a voltage difference with your prep to breadboard. To make sure the power always stays delivered, I'm going to make a suggestion of a little simple circuit that you can build that helps with just keeping an eye literally on what's going on. So the next thing I'm going to do is to, as I'm building it, just leave my voltmeter in place reading 9 volts across. That means I can tell I'm always getting power down to the other side of the board. And I build a very simple battery, resistor, and LED circuit. So just like a very first circuit, except now on the breadboard. So diagram is at the top left-hand corner, putting a resistor and LED to ground. Look, I've used a blue wire to indicate the ground. The resistor lead goes directly into the upper red bus board, and the LED straddles the break between the 2 horizontal bars. Make sure you understand how this is wired together. I really strongly suggest building several small little lit LED circuits in various configurations. There'll be an assignment question about configurations that don't work. All right, now we're going to actually go and build a simple LED switching circuit, again, just to practice breadboarding. So here's the diagram that I'm going to build in the lower left-hand corner. You can see the slide switch is acting like a toggle. There's a single resistor that goes to the center pin of the toggle switch. Now, slide switch. Now, notice when you put that slide switch in, it has to be put in so that each of the 3 pins is in a separate row. And notice how the outside 2 are getting connected to an LED. And just for clarity, I'll use a green and red LED. The resistor will go from high to the center pin, and then we're going to use some blue jumper wires to send the short lead of each LED to ground. So trying to resemble my picture there as much as possible. I can actually check the circuit was partially built. I should be able to turn on my right or red LED yet by pushing the toggle switch over the proper side. But of course I have to wait till I actually ground the short end of the left or green LED until it's fully functional. Note how that jumper wire goes in the same row as the LED leg, but then it can go anywhere convenient along the bus board. And of course, in case of problems with attaching my battery leads, I've always got as a check down at the other end of the circuit my very simple 1 LED indicator telling me my power is hooked up and everything is working. Let's check the circuit out, make sure it behaves as expected. Grab usually a non-insulating pencil and see I can go from red to green and back by gently pushing that switch. Again, the circuit that's at the right hand of the board is just to let me know I've got power on. Completely optional. It's just a simple test circuit. I'm going to do a little modification, which is to put in a toggle switch. And I'm actually going to clip the leads down so I can push my toggle switch, leave enough length so that I can actually get it in. I'm going to bring the resistor over to a different row. So this, of course, now means that my circuit is no longer functional until I connect that resistor in the same row to power, but I'm going to do that through my toggle switch. You have to spend some time usually getting your leads at a good length. It's almost always necessary to cut the leads down on the toggle switches to get them to work. So again, applying a good amount of pressure, getting the leads at the right length. And now I'll bring the power down to the tactile switch. And so when I press it, then I'm able to get the color of the LED that I have selected, either the red or green, either the left or right, but only when I press the button. Let's just take a few minutes and follow the path of the current through the circuit. Do check again, make sure all of your connections are nice and solid. Things will get more complicated from here. So starting, the power comes in from, in our case, the bottom of the breadboard, jumps over, runs across, goes through that red jumper to one side of the switch. If the switch is pushed down, it runs up the breadboard rail through the resistor over to the center pin of the switch, and then if say our switch is pulled left, it goes through the long leg of the LED up over the break down to the other side and through that blue jumper cable back to ground via hopping back over the breadboard. Seems like a circuitous route, but notice how clean the layout is because I've set things up. Let's just check the other side's layout. It works. When I again press the button, now I get the red light. Let's follow the power path again. Coming in from the battery, jumping over through the tactile switch, through the resistor to the center pin. Now, because the switch is on the right side, through the red LED, back to ground and around to the black lead of the battery strap. All right, a first nice circuit on a breadboard. We're going to move over to the main part of the chapter now that we've developed some breadboarding techniques, which is to build a relay switch and then a relay oscillator. So go ahead and pull things out of the breadboard. Sometimes those needle nose pliers come in handy. And take a look at the diagram. We're basically doing the same thing, which is turning on and off LEDs, but through a relay. A little hack I'm going to show you here is to use a rubber band to help keep those pesky terminals from falling off. Now, shown in the lower left-hand corner is a really great diagram from the textbook. It shows an X-ray view of the connections we're going to make in the circuit. So you've got two different ways of representing the circuit. On the top is the circuit diagram, which is not going to look exactly like on our breadboard. And the bottom left-hand diagram is this X-ray view of what's actually going on in the circuit. Now, the textbook tends to give you lots and lots of layouts in this breadboard format in the lower left-hand corner. Keep in mind that that's not a fundamental way of representing the circuit. There's many, many ways that you could wire up a breadboard to have the same function as a circuit diagram on top. We're going to start off by, in the video lectures, often trying to follow the book's arrangement of particular components on the breadboard for clarity. I'm also going to be pushing you on the assignments and later on the course to come up with your own arrangements that look very, very different. So keep in mind the schematic on the upper left-hand corner is the one you could share with the rest of the world. They'd understand what you were doing. The one on the lower left-hand side is just a layout and not so important. So you can start, if you wish, by just following along with the layout in the book. Here's another version of the same figure in the lower left-hand figure where the author has added in all the spurious or unused rails and buses that are in the breadboard. Notice that, of course, we're only using components checked on them. Please spend some time following through that path in your head, as well as the schematic diagram, rather than just blindly wiring up what's done. So we see we've got two LEDs. I'm again going to use red and green just so it's easier for me to talk about in the video, but feel free to use two red ones if you wish. The author's diagrams more typically presume that you understand what's underneath the breadboard in terms of format, and so he usually just shows you that top view with some symbols on them. It can be tricky to get the relays and some other components with lots of pins in and out of the breadboard. So do make sure that the pins on the bottom of your relay are properly straightened out. I have put a schematic version from Lush Projects in the upper right-hand corner that shows what exactly our circuit does, which is to toggle between which LED is on based on making the contact of the relay. You can see when I press the switch, current flows through the relay coils, and as the switch is thrown, it diverts the current from one side to another, lighting up the red versus the green LED. Occasionally taking out components, making sure the pins are straight. Notice that the push button tactile switch depends on the orientation you put it in. You can put it in either vertically or horizontally. To go to the next experiment, which is actually building an oscillator, you have to rotate the switch. And notice how I'm now putting the switch in a different orientation. Now this next circuit, the idea is that we're actually connecting the output of the relay to the control. So this would be in sort of an unstable state where when it flips the switching turns on one LED, it then immediately turns itself back off and vice versa. And so this is done with just a simple change in the position and the addition of an additional jumper. Now when I have a jumper which is going to be changing state, from say on to off and back and forth, I'll try to not make it say red or blue or red or black, but a different color. I think there's green wires in the first kit for most of them, so I'll just use a small green jumper. And notice how I have to really get things in the proper row of each breadboard. I can choose to have a different hole along that row, but it's got to be in the right row in order to work. Now when I press it, I should hear a buzzing. And that buzzing is that oscillator unstably switching between two states really quickly goes to the green LED. We can't even see it because it's so fast in the back. And it makes that bit of noise. To slow it down, we're just going to qualitatively explore what happens with a capacitor. By the way, don't hold down this relay too much. Without the capacitor, it can burn it out. Caps, which we'll talk about, they'll be the whole subject of Experiment 9, are like LEDs if they're electrolytic capacitors, and this 1000 microfarad, which would be a millifarad capacitor, has a long leg and a short leg. The long leg also goes to the positive end of the circuit. There's also indicator along the side of most electrolytic capacitors, which has minuses written on it. So I'm put the capacitor actually across the control current coil of the relay, and we're just going to observe how it slows things down. So make sure those leads aren't touching each other, any exposed components. This is why you should, where possible, try to cut leads so that they don't have any exposed conductive parts above the surface of the breadboard. And here's a little diagram. By the way, if you do try to draw this, up there it goes. It's oscillating, but a lot slower. Now we can actually see the green light come on because it's slower. If you're going to draw this in Lush circuits, you may find the configurations doesn't look quite like it does because they're relays of different terminals. You have to add the capacitor in order to get the oscillator to work in the simulation. High frequency buzzing becomes a low frequency switching. Let's try some other capacitors. Here's a 100 microfarad. I think all kits have this. You can put it in with the proper lead polarization. And this is going to slow things down a bit, but not nearly as much as the huge capacitor. You can still see the lights flashing, but a different pitch. going at some intermediate rate. We can try even yet smaller capacitor if we wish. I think I'll try a real small one, a 1 microfarad, still electrolytic capacitor. Again, leads come in the same configuration, long towards the plus, short towards the minus. Put that right across the relay terminals again. You can see the pitch doesn't change too much, but it does make it a little bit quieter. We'll talk more about how capacitors work next time. The assignment for Experiment 8 is, first of all, to use the circuit simulator to do some very simple switch circuits and actually breadboard them. So simulate them and then put on a breadboard. I'd like you to make a manual switch stoplight using 2 slide switches. Just like either red, yellow, or green LED, just like a stoplight. Make sure you include, of course, the current limiting resistor. 1 current limiting resistor placed at the proper place should be enough for the circuit. Please put a photo and a screenshot of the simulation in your logbook. Second thing is go through what I was doing at the end of this video and investigate that relay oscillator with different capacitors. Try an experiment suggested by the textbook, which is removing the right-hand LED, that was the green one in my video, while leaving the large capacitor in and pushing the switch. Describe what happens. We'll talk more about that next time. Then finally, look at the incorrect circuit. Don't build it. It's in figure 2-76. Try to explain what it is that does it wrong and attempt to draw by hand a circuit diagram of what would actually be the configuration should we try to make this incorrect circuit. Make sure you understand what's wrong with figure 2-76.